Hello everyone. Today we are going to start learning about acids and their chemical properties. Um, so by the end of today's lesson, I hope that you'll be able to identify acids and bases by their formulas and properties, predict how acids react with water, and determine if an acid is strong or weak based on its Ka value, K being the equilibrium constant, and A signifying that it's for an acid. We'll learn a little bit about that later. Okay, so let's start off with what you might already know about acids. Um, Acids, most people know, are part of your stomach, and they're an important part of digestion. Okay, your stomach is a very acidic environment. Um, a similarly acidic environment you might not know is a lemon. Citrus fruits are also very acidic, and that's what gives them their sour taste. So one of the properties of acids that we got to see in the lab is that acids are very corrosive, especially to metals. If you remember, they even have the power to dissolve metals. Um, they don't always have the same effect on other substances. For example, most acids won't dissolve paper if they're dilute, but even if they could dissolve metal. Um, so, the chemical properties of different substances determine how corrosive the acids would be, but concentrated acids are very dangerous. I really like this symbol of a hand. This is found on many concentrated acids. It shows that the acid is corrosive to skin. So most of you know that acids can burn skin. They are certainly toxic if ingested um, in concentrated form. There are plenty of acids we eat on a daily basis. Vitamin C, for example, is an acid. So not all acids are harmful, and certainly the concentration determines how deadly anything could be. Another property is that they turn litmus paper red. Litmus paper can come in three varieties. Typically, it comes in blue or red litmus paper. So if we wanted to turn it red, we would use blue litmus paper, which would turn red in contact with acids. There's also universal indicator, which is yellow paper that would turn red in the presence of acids. So these are a couple of properties for identifying acids. The next time you eat something and it tastes sour, you can expect that there's probably some kind of acid in that substance. So let's look at what it actually means to say that something is acidic, right? So I mentioned your stomach is very acidic. Svante Arrhenius, in the late 19th century, came up with a definition that we still use today. An Arrhenius acid is defined as a substance that produces hydronium ions, which are H3O+, when reacting with water. So an acidic environment would be an environment that contains a higher than average amount of H3O+. Okay, what's a higher than average amount? Well, neutral environments have a concentration of H3O+ equal to 10 to the minus 7 moles per liter. That's very low. Okay, so anything more than that is considered acidic. Your stomach, for example, is around 0.01 molar, or 10 to the minus 2 molar. Okay, much more acidic than neutral. Right? And some substances that we might use in the lab might have a concentration of 1 molar or even higher. So let's look at how these substances actually produce H3O+ when they react with water. We're going to look at the most common example, and that is HCl. HCl is hydrochloric acid, easily attainable, it's pretty stable. We use it in the lab all the time. So when hydrochloric acid reacts with water, one of the products is H3O+. I want you to look at that equation, see if you can figure out what would have to be the other product in order to keep it balanced. Right? All that's left over is the chloride ion. Note the left side of the reactants, they are neutral. So the products also have to add up to a neutral charge. So one positive product, one negative product. Let's look at another one. Sulfuric acid is another common acid. Okay, when it reacts with water, one of the products is, again, H3O+. This one's a little trickier. See if we can figure out what would be left over. Okay, the leftover ion is called bisulfate, HSO4-. Okay. So these are some examples of acids reacting with water, and they all react in a very similar way. One thing that I want to note is these reactions can be simplified, and they often are, just to make it a little bit easier to write. Okay, so for example, HCl reacts with water, could be simplified like so, to show that HCl dissociates into H plus and Cl minus. Okay, so that's a simplification of that first reaction. I mentioned that it's a simplification, but it's not true to reality. The first equation is truer. Okay, H plus ions don't exist alone in an aqueous solution. They do exist as hydronium ions, H3O plus. But what did I cut out of this simplification? Right? I took water out of the equation. Okay, so H3O plus became H plus. The H2O on the reactant side was entirely removed. Okay, this simplification, you'll see me using it often. I don't mind whichever way you want to use it, as long as you can recognize that when I say, or when you're writing H plus, it really is a hydronium ion. It's not just a hydrogen ion by itself. Okay, but again, you'll see me using that plenty of times. I want to give you one more example, and this is just a very generic example. So one of the things you might not have noticed, acids start with a hydrogen. Okay, whenever you see a substance that begins with H, we can assume that that is an acid. There's another acid in those equations as reactants that you might not have noticed. Okay. Right? Water actually can behave as an acid. It's not behaving as an acid in these reactions, but it does behave as an acid in some other reactions that we'll see next time. And it starts with a hydrogen. Okay, so plenty of substances have hydrogen, but the hydrogen is not written first. Okay, we can assume that those are not acids, but when we see hydrogen written first, we're going to assume that it is an acid. So this is a generic form for an acid, HA, where H is the hydrogen and A could be a sulfate, chloride, iodide, whatever other negative ion would pair up with it. Okay, and it would dissociate into H plus and A minus. That would be the simplified form. Or we could write the full form reacting with water to form H3O plus and again A minus. Okay, this is a generic expression. Okay, it's useful though to keep in mind as you're looking at other practice problems. They should follow this pattern. Okay, so that gets us to our more modern definition of an acid. It's a little bit more comprehensive. So I want to keep those generic expressions so you can see them. Okay, our definition that you'll see in your textbook is a Bronsted-Lowry acid. And this is defined as a proton donor. Okay, so I want to look at what HA is actually doing. What's it doing to the H2O? Well, it is giving one of its H pluses. And if we remember, hydrogen atoms are made of a single proton surrounded by an electron. Okay, if I were to take that electron away, all I would be left with is one proton. Okay, an H plus ion is simply a proton. So when I say a proton donor, you can also think of that as an H plus donor. Okay, the Bronsted-Lowry acids give H pluses away. Typically, they give them to waters, but they can give them to other things. Bronsted-Lowry bases accept protons. For example, in the equation above, H2O starts with 2 hydrogens and it ends with 3 hydrogens, right? So it's accepting a proton. That makes it a Bronsted-Lowry base in that reaction. Okay, so let's look at one. See if you can try this on your own. H3PO4 reacts with water to produce. Okay. Should take a moment, see if you can figure out what the two products would have to be for this. Okay. Hopefully, you realize that the first product is, of course, hydronium. The second product is called dihydrogen phosphate. Okay, so that is a Bronsted-Lowry acid, phosphoric acid, giving one of its hydrogens away to water, which is acting as a Bronsted-Lowry base and is taking that proton. Okay, these two things always come in pairs in the reactions. One thing gives, the other thing takes. Okay, so up until now, we've been writing these reactions as if they're only one direction, unidirectional reactions. Turns out it's not entirely true for many acids. They are reversible. And remember, we write reversible reactions with that double arrow. Okay, that is to say that a hydronium ion, dihydrogen phosphate, can also react again to produce the original phosphoric acid and water. So I want you to see if you can write the K equilibrium expression for this reaction. Okay, so let's jump in. So K for this reaction would be the concentration of the products, hydronium, dihydrogen phosphate, in the numerator. The denominator is our acid and water. Okay, so this is our equilibrium constant, or it would be our reaction quotient if it weren't yet at equilibrium. But like I said, we'll typically assume equilibrium's been reached. So here's our equilibrium expression. As I mentioned above, we can simplify our reaction to not include water. K in this expression does include water, and that's fine. But water has a very high concentration. Its concentration is actually it's actually a little bit higher than 55 moles per liter. That's very high compared to the other concentrations we typically use around, say, 0.1 or 0.2. So for all intents and purposes, H2O is essentially a constant. And if we ignored the H2O as not being a variable and taking it out of this expression, we get a new expression. We call this the acid equilibrium constant here, denoted with an A there to indicate that it's not just an equilibrium constant, but it's an equilibrium constant for an acid dissociation. Okay, this uses the simplified expression, which does not include H2O and includes H plus in place of hydronium. Okay, so this is going to show H plus dihydrogen phosphate in the numerator, and the denominator simply has the phosphoric acid. Okay, makes the expression a little bit simpler. And this is our expression for the acid dissociation constant. For phosphoric acid, it is about 0.007. Every acid has its own acid dissociation constant. And these constants could be looked up online or in tables. Like I said, they're readily available. The Ka value for phosphoric acid, it's pretty low. So I want you to think, what does that mean about the ratio of products to reactants if the Ka value is much less than 1? Okay, hopefully you noticed. This is going to be in the majority. We will have the majority phosphoric acid left over. In other words, mostly reactants. it turns out for this particular reaction, you're going to have greater than 90% of the substance will remain as reactant, and less than 10% will actually dissociate into hydronium ions and the dihydrogen phosphate. Okay, so we call acids like these that don't readily react with water weak acids. All right, so we get a little bit more space here. Okay. So weak acid is an acid that does not dissociate readily in water. Okay, so actually do it over here. Okay, so say it dissociates partially in water. Okay, typically it dissociates to a very small amount. Phosphoric acid dissociating about 10% is actually relatively high for a weak acid. Many of them dissociate 1% or less. Okay, so they have Ka values that are much less than 1. Okay, some of them range, could be 10 to the minus 2, like phosphoric acid, down to say 10 to the minus 7. We could even measure some that have phenomenally low ones, like 10 to the minus 30. That would be a very, very, very weak acid. Okay. In contrast, a strong acid dissociates fully. In other words, all of the acid reacts with water, is effectively a one-way reaction. Okay, we can assume that all of the reactant becomes product, and we end up with Kas that are much greater than 1. An example like hydrochloric acid has a Ka value of around 1,000,000. Okay, think about what that means. To have a Ka value of 1,000,000, the numerator, the products, has to be much, much higher than the denominator, the amount of HCl left over. We wouldn't even really be able to measure how much HCl is left, still bonded together as HCl in a high school lab. Okay, all right. So weak acids, they have very low Ka values. We would need to actually solve to determine how much of it reacts based on the Ka value. Strong acids, on the other hand, they're much easier to use mathematically. We often represent them as one direction, unidirectional reactions, just simply under the assumption that all of the reactant becomes product. Right? Because if we're talking about a Ka, around 1,000 or 1,000,000, then, for all practical purposes, all of the reactants become products. When we're talking about an acid that is weak, we like to write this as a reversible reaction. Okay, and it is important then to determine how much of it actually reacts. Remember, in order for it to be acidic, it only needs to form enough hydronium ions to increase the concentration beyond 10 to the minus 7. So even if 1% of it reacts, that's still enough to make the environment quite acidic, okay, as it is in your stomach. So we'll look at how these reactions actually, how acids actually react with bases in the next video. But if you have any questions, please let me know via email or Google Classroom. All right, have a good one.